video we're talking about how to use part 2 of the fundamental theorem of calculus, and part 2 of the fundamental theorem is actually used much more commonly than part 1, and really all it does is define the definite integral. So part 2 of the fundamental theorem of calculus is this formula right here, and it tells us that if we take the integral of a function, we'll call that function f of x, we take the integral with respect to x, that's what dx means here, take the integral of this function with respect to the variable x. So we're integrating that, and we're going to evaluate the integrated function over the interval x equals a to x equals b. Doing that is the same thing as this right here. Notice the capital F versus the lowercase f. Lowercase f is the original function we start with, the function itself. Capital F is the integrated function, or the integral of lowercase f. So once you find the integral of f of x, you'll have a new function, and that'll be capital F of x. And then all you need to do is plug b into that integrated function, that capital F function. B is called the upper limit of integration because it's the upper end, or the right-hand side of the interval a to b. So you plug that in, and then you subtract whatever you get when you plug a into capital F of x. So using this theorem is as simple as this. We've been given this problem here. Find the integral of cosine of theta d theta over the interval pi to 2 pi. So first of all, the variable in this question is theta instead of x, but don't let that throw you. This is just a function in terms of x, and it says integrate with respect to x. Well, here we have a function in terms of theta, and it says integrate with respect to theta. So it doesn't matter what we call the variable, whether it's x or theta or something else, the fundamental theorem is still the same. In this case, a is equal to pi, and b is equal to 2 pi. So all we need to do is take the integral of this function, cosine of theta, and we're going to ignore these limits of integration, pi and 2 pi for now. So the integral of cosine of theta, and remember the integral is the same thing as the antiderivative. So if we think about derivatives for a second, if we start with sine of theta, we know that the derivative of sine of theta is cosine of theta. If we take the derivative of cosine of theta, we get negative sine of theta. And if we take the derivative of negative sine theta, we get negative cosine theta. So these are our derivatives. Well, the integral is the same thing as the antiderivative, so it just means we're going in the opposite direction. So if we're starting here at cosine of theta, because that's the function we start with, we're just going in the opposite direction, and the integral is sine of theta. So when we say the integral of cosine of theta, that means the result is going to be sine of theta, which means our new function, our integrated function, capital F, so we'll call this capital F of theta, our variable, is going to be sine of theta. Now, since that's our new function, we're looking for capital F of b minus capital F of a. So all we have to do is plug b into this function here for theta, and then subtract whatever we get when we plug in a. So if we say f of b minus f of a, that's going to be equal to, let's plug b into this function. Well, b is 2 pi, so we're going to say f of 2 pi minus capital F of a. In our case, a is pi, so we're going to say minus capital F of pi. And when we say that capital F is sine of theta, we can say here sine of 2 pi minus sine of pi. And now we just need to simplify. So if we look at our unit circle, or if we plug this into our calculator, as long as our calculator is in radian mode, not degree mode, sine of 2 pi is 0, so we get 0 here. Sine of pi is also 0, so we get 0 minus 0, or just 0, which means that the value of this definite integral is going to be 0. Now remember, the integral is just the area under a curve. So if we were to graph cosine of theta, let's conceptualize this for a second. If we were to take an xy coordinate system here, so we have our graph, and we say x and y axes, we'll call this 0, and then we'll mark off here pi over 2, pi, this is going to be 3 pi over 2, and this will be 2 pi. So if we graph the original function, cosine of theta, when theta is 0, we get cosine of 0, and cosine of 0 is 1. So we graph this point here at 0, 1. When theta is pi over 2, we get cosine of pi over 2, which is 0. So we get pi over 2, comma, 0, and we graph that there. When theta is pi, we get cosine of pi, and cosine of pi is negative 1, so maybe that's about right here. cosine of 3 pi over 2 is 0, and cosine of 2 pi is 1 again. And you can see that using your unit circle or if you use your calculator. So if we just graph this, it's going to look something like this. So we've graphed our original function, and remember that when we take the integral of a function, we're interested in the area under the curve, and because we've been given the interval pi to 2 pi, we're really interested in the area under the curve on the interval pi to 2 pi. So if we look at that interval, here's pi, so we'll go ahead and draw a line here, pi, and then 2 pi, so right here, this line through 2 pi. So what we're interested in is the area under the curve, which we can see is going to be this area right here and this area right here. You can think about it as the area enclosed by the graph and the x-axis. So that's these two sections right here. Well, what we can see is that these two sections of area are equal, and because one is above the x-axis and one is below the x-axis, they net to 0. The net area is 0, and when you're asked to find the area under the curve, you're really being asked to find net area, which is why we got an answer here of 0. So when we're talking about part 2 of the fundamental theorem of calculus, all it says is that one way to figure out the area underneath this curve f of x over the interval x equals a to x equals b, the way to find the area under that curve, or the integral of that function on this interval, is to take the integrated function, or the antiderivative of lowercase f, that's going to be capital F, plug the upper limit of integration into that integrated function, and then subtract whatever we get when we plug in the lower limit of integration to that integrated function. And that difference right there, capital F of b minus capital F of a, that difference is going to give us the net area under the curve. In other words, part 2 of the fundamental theorem just tells you how to find the area under the curve. It defines what a definite integral is. It tells you that a definite integral is just the area under the curve on the interval a to b. And therefore, whenever you have a definite integral, you're just using part 2 of the fundamental theorem to find the area under the curve, or when you're asked to use part 2 of the fundamental theorem, all you need to do is integrate this function and then evaluate over this interval.
Could you use some extra help with math? Click the button to head over to calculusexpert.com. It's where I've collected and organized all of my best resources, including exclusive videos, notes, quizzes, and even formula sheets. It's the perfect resource whether you're struggling, or if you want to take your learning further, or even if you just want to save yourself some time studying. So check it out, because I know it'll help.